Yeah, thank you for the kind introduction, and it's great to be here again. Today we want to talk about the journey at Chrono24 from a recommendation engine based on collaborative filtering to a recommender system that is based on embeddings and uses NLP techniques. So we will first start with some short introduction to Chrono24 and the data we use for that system. I will show how we started with the first recommender engine. What limitations there in this system, and what we thought about and how we wanted to solve these limitations, and finally how we built and constructed the model and trained it. Okay, so I will skip the CV part because you can check us out on LinkedIn. But I will briefly talk about Chrono24. So Chrono24 is the largest marketplace for luxury watches. We have 25,000 professional sellers and private sellers on our platform from 120 countries. We are a true international marketplace. That means that we have a lot of cross-border sales on the platform. And we have 4 million registered users, 500K listings usually online on the platform, and 9 million visitors a month. And the gross merchandise value in 2020 was like 2 billion. So our data team is about 20 people. We have data science, machine learning engineering, business intelligence, web analytics, and data engineering. And our tech stack, just to mention it, is like Snowflake, dbt, TensorFlow, Python, and Pandas, typical stack, basically. So if you buy a watch on Chrono24, you can imagine that if you buy a luxury watch, which is like 10,000 bucks or something, you take more time to research and to hunt for that what you want to buy. That is good for us. If the user is willing to share his information with us, then we can collect all the data, all the not transaction, but clicks he does on our website, and we can build up this session data, and finally we have 2 terabytes of these sessions collected. And in this data, there are roughly 11 million different listings which were at some point online on our platform. A typical user session is 5 minutes and 16 seconds, which is quite short, but it's the average, so might be a different experience if you browse on Chrono24, and typically a user clicks at 5 listings. With that data, we first started with a collaborative filtering approach from Amazon. That it's, I think, quite popular one. And what we do here is we map each listing on our platform to a product. And this product is defined by the reference number of the watch. So it's like a product identifier, basically. And with that data, we assume that our users know what's similar. And the idea is basically that if a watch is clicked with another watch in the same session, then these watches are similar to each other. That's the idea. That's something we built, I think, 6 years ago. And finally, we have a product metrics and calculate the cosine similarity between these rows, and then we finally get to a point where we can get similar products for every product. For actually getting results for the user, we have to map back from our products, so the reference numbers, to actual ads on the platform, listings on the platform. And for that, we score the user interest. So we have several different sources of where the data came from, like the user history, the favorites, what he marked, and stuff like that. And we score them, map back to the listings, score the listings again, and basically produce a recommendation for the user. So this is the system we have built at first. And it was, when we released this, one of the most engaging elements on our website, so it worked pretty well. But there are two limitations to the system. So one is a technical one, so it's more that with the recommender system, we wanted to build a feed, an infinite personalized feed on our app. And with that, it wasn't possible because of performance issues and stuff like that. And the second reason, the second limitation is that we have our watches sometimes don't have the necessary data to do the mapping from the listing to the product, which is necessary for the recommender system. And therefore, I will just go into how that works in the luxury watches world. So usually if a watch has the same reference number, then it's the same watch. So that's the idea. It's like a product identifier, but this is not true every time. So every manufacturer has its own scheme how to produce these reference numbers. And sometimes they do not encode every detail of the watch into that number. So it can happen that you have a watch that has the same reference number on paper, but it's actually not the same watch because there are diamonds on it or stuff like that. And it makes it pretty difficult to recommend the right items. So on the other side, we have the users. They have to input their reference number correctly so that we can map it. And of course, there are sometimes some misspellings, errors, and we try to fix them, but it works not every time. And in the end, we end up with 30% of our watches which are not mapped to a product, and therefore we cannot recommend them in our system. And we want to recommend them. And that's why we thought about it, how we can solve that. So the idea is that we don't rely on our product mapping, but we want to map our listings directly into a vector space where we can use these embeddings to measure similarity directly between these listings and ads on our platform instead of relying on having the requirement to map the product. And with that, we can basically calculate means and clusters. We can build up an approximate nearest neighbor index to search very fast through all these listings. And that was basically the idea, what we ended up with. And Florentin is now talking about how we constructed that model and how we trained it.
So let's talk about how we solved this problem. So some of you might guess where we are heading now, seeing Elmo and Bert here. But just to clarify something, first, we are not talking about Bert for rec here. It's not a topic of this presentation. We are talking about the red box here. So here you can see the full overview of a recommender system. And what we want here is, or what we are talking about here, is the red box. So we want embeddings, we want an approximate nearest neighbor index. That's what we want to build. But there is some connection to Bert. And basically, that's we use Bert as a role model, but not the first task, the masking task, which is using Bert to rec, but the second one. So the next sentence prediction so we use the next sentence prediction as our baseline to train a model. And our sentences are basically represented by ads on our platform. And the model predicts whether two ads are in one sentence or not. So is it in one session or not. So we're looking at the user sessions as the training data, and we see, okay, are they in the same session or not? And the words of the sentence are attributes from our ads. And I will show you some examples here now. So we have example ad here, Grand Psycho Snowflake watch, and there are several attributes in all of these listings on our platform. For instance, we have the caliber, the price, the country, it's from the US. And actually, we had interviews with our customer to select these attributes. So for instance, I at first thought, okay, we don't need the country. So why is it important? You can buy it from anywhere, like globalized world, stuff like this. But this, like Kristen said before, it's very important because of toll and taxes. You have to take care of it. And hence, there are some relations to the country. And it's a very important attribute here. And furthermore, we have to discretize the continuous values, like the price. So we have to say, okay, we don't use the continuous values here. We do something like price segments, low price segment, mid price segment. We have some business logic behind it. We use it also for other models, and we reuse it here. And then example sentence would be something like this. Okay, we have the Grand Psycho Snowflake, new condition, box paper, stuff like this. Number of jewels, mid price segments, and it's from the US. So in the end, the model would be trained like something like this. We have the sentences, so the attributes from our ads, the brand, Grand Psycho, the model, Snowflake. Then an additional, so 2 sentences, because we want to train them. Are they together somehow or not? We feed them into the transformer model here, the bird, and then train it on this task. So in this example, we got an Apple Watch and the Grand Psycho Snowflake that I showed you before, and they are like not seen in the same session. So that's what the model predicted here. So to sum it up, the training details here, we just collect the relevant session data. So to train the model, we convert the ads into the attribute sentences I showed you before. And then we train the embeddings by predicting if the ads were viewed within one session or not. So that's what we did, and actually it worked quite well using this transformer model, but we did some additions to further improve the performance. So I'm going to the implementation details now. So instead of transformer model, we actually used a time-distributed one-dimensional CNN because it turns out it's more lightweight than the transformers and actually had better results. And we also not directly used the transformer task, but also adapted this we fed our input, the attribute inputs through this model and to get the embedding vectors. And then we calculated the distance between them. And then we say, okay, hey, if they are close together, the distance between our 2 vectors has to be somehow 0, so they are viewed within one session. They have to be close together in our embedding space we're creating afterwards. And if they are randomly sampled, we say they have to be a bigger distance between them. So basically, the distance between all our vectors is mapped between the space 0 and 1. And if they're close together, they are 0, and if they're further apart, they are 1. And hence we say, the label are 0, viewed within one session, 1 if they are not. And we also have some business logic regarding the sampling, so they are not completely randomly sampled, because if we just randomly sample 2 ads, but we know, okay, they have the same product, said before, and then we know, okay, they are very likely, or they should be very close together in the embedding space, hence we can resample there, and we have some business logic in the random sampling. So that's what how we further extended our models and improved our results here. And now I will show you some results. So let's go there. So what you see is if we input the attributes of our example from the Grand Psycho, we see that we get very close ads here. So they are very similar to the input ads, like the same price. It's basically the same brand, same dial, same country, all this stuff. But furthermore, if we we see if they're not like that, that many ads. We see there's also another watch has a different reference number, different product, but very close together, like which basically is the same watch more or less, but a blue dial and some other different changes like a bracelet. But that's like one of the advantages we can use when we sample it there in the embedding space. And there's also another comparison with the old recommendation. So if you use this ad and the attributes of this ad as the input in our new model, and just look, okay, which cool related products do we get and which ads from there, we see we have very close watches here. So they are all the same movement, more or less, the same brand for sure. So we see there is a huge relation between those results we see and the thing we input. And the old approach has some good results here, the grand cycle, but also some watches which are not related anyhow. You also can see a huge visual relation here, even though we didn't use any images as an input for the model for some reason, or for there, because we've had some issues with the images here. And additionally, there's another cool thing you can do with that approach, and basically the model can work somehow as a search engine. And I will show you some example here. So for instance, we have those attributes as the input, the Steinhardt Ocean 1, which is the brand, the model, and then something like steel case, steel bracelet, low price segment, and the country. And what you see here is, this is basically the one you would imagine to get from our platform. But let's say, okay, there's only one listing from France there. Then the next listing is from the Netherlands, which is also very good because everything is in the European Union, so you don't have any problems buying it from the Netherlands as well, even though you said, okay, you want it from France, but there are just no listings left. And now let's say, okay, we change the country and the color. We say, okay, as input, we use the blue bracelet, blue dial, blue bezel, and say we want it from the US, and then we get these results. And also note here that we don't have a blue bracelet here, but still it's very close to the original blue bracelet we had as an input, and still similar also in price. So still good results if you have nothing else to show. And the third last result is, okay, let's say we got a raise. We have more money to spend on luxury watches. Let's change the price segment to the high price segment. And also we don't care about the brand. We just mask that one. It's also something you can do like from Bird, from Bird, just masking the input, so the model is more robust. Let's see what do we get here. And we see, okay, we got the Oyster Rolex sub with also a very beautiful blue dial. It looks very close to the original one. You can guess which one was there first. Probably, and yeah, that's I think a pretty cool thing you can you get from this model. So to sum it up, why embeddings are cool? We have endless similar items we can get, and they're very close together. We built a feed with those lists and got a quite good user rating of 4.3 stars and very high uplift on all of our core metrics. We have no cold start problem, so there are a lot of solutions using images to solve this cold start problem. But if you just use attributes, you can encode every new listing there. And sometimes there might be new brands or new attributes, so you might have to retrain it. But in the end, the model is very good in handling unknown input. So even though there's a new brand and it's just an unknown token in your input, and the model can handle it. You can change the attributes dynamically, like I showed you before, and using like a search engine or further personalize the output. And okay, and furthermore, you can, it's a thing you can do like during the training. If you want the model to overfit on special attributes, you can also do this. So for example, you have an input, and they are both close together, but you see in the attributes that they don't have the same country. You can just increase the label for 0.1, so the model learns that they are not that close together, and hence you get like an overfitting on the country if you want the model to focus on that more. And that's basically it. Thank you for your attention, and I hope you enjoyed the talk.